All right, so we're going to start talking about ionic compounds, and in order to understand them, we're going to show you the process of formation of these ionic bonds. And this is going to be on pages 5 and 6, but it's really just one page. It's the bottom half of page 5 and the top half of page 6, so this shouldn't take long. Now, down there at the bottom of page 5, you have the instructions for what we're going to be doing here. So it really is a kind of 3-step process that's showing the full process of formation. And sometimes, like the district people might just ask you for one part of this process, but it's important we understand the full thing so that we can, do any part that they ask us about. And so our first step in drawing a compound's Lewis dot diagram is actually going to be to draw one Lewis dot diagram of each element separately. And in the future, we're going to learn some tips and tricks on how to write the formula of a compound, and that'll tell us how many of each atom of each element we're going to need in that compound. And so once you learn how to do that, that might be a good thing to do here, because sometimes we need more than just one of each atom. And knowing that ahead of time can make this process a little bit easier. But we'll get to that. And we don't really need that in order to be able to do this process. And a lot of people don't do that part correctly. So this part can really help you maybe figure out that part. Now, a couple of quick reminders about drawing those Lewis dot diagrams of our elements. Every element gets one dot around them for every valence electron that they have. And we can find the number of valence electrons that an atom has based on its position in the periodic table. Remember these labels? The labels that have the A at the top of each column remind us how many valence electrons those elements have in their column. And these elements don't have an A label at the top, not because they don't have valence electrons, but because they don't follow the same normal rules, and so we can't really predict their valence electrons. So that tells you how many dots to use. And then remember that we put one dot on each side of the element's symbol. So if I had like Cl, which needs 7 dots, I would put one dot on each side before we start doubling up. Now, for chlorine with 7, no matter how or where you put them, they'd all end up with 3 pairs and 1 single. But if I had something like boron that needs 3 dots, it is really important that those 3 dots go on 3 separate sides. So you start off by drawing your separate elements based off of the elements you're told are forming this ionic bond. And then your second step is going to be to use arrows to move those electrons, because they aren't going to stay in one place as this reaction happens and our compound gets formed. And so it's really important that they start at a specific electron and they go to a specific empty spot. That's the whole idea here. Is there's some atoms that want to get rid of their electrons, and there's some atoms that want to get more electrons and fill in some of the empty spots in their Lewis dot diagram. So we need to specifically show which electron is going into which empty spot. Now, if you've written your chemical formula up in step 1, you should have all the atoms you're going to need. But there's a possibility where you might either run out of electrons or empty spots. And if you do, you need to draw another atom that are going to get you those spots or get you those electrons, because every atom has to end up completely full or completely empty, one or the other. It doesn't matter which in general, but everyone has to be completely full with 8 electrons or completely empty with 0 dots, 0 electrons around it. So that's the key with step 2. So this step 2 can last a little bit as you keep adding electrons and moving them around. But once you get all the atoms full or empty, you've technically found our compound's formula, and we're going to redraw all of those atoms with their new electron. So we're going to draw them as full and empty with their charge in the top corner of these little square brackets that we're going to put around them. Now, when we have more than one atom of the same type that are involved in this process, you could draw them more than once, or you could just use a coefficient, a number in front of that ion, to show that we needed more than one. And it's kind of up to you. I'll accept it either way. So I think the best way to get this process is to see a couple examples. So I am going to work a couple examples on the next page, and I'm going to consistently color code this step 1 where I'm drawing the individual atoms in purple. Then I'm going to draw my arrows in blue, and then I'm going to do my final step 3 in green. And I think that really helps you see this process, and especially if you're going back to look at your notes before a test, that color coding could help you as well. So if you can find 3 different colors to use on this next page, just like I am, I would encourage it. So, one last note before we leave. Remember that when we're putting those charges in the corner, that positive charges come from losing electrons and negative charges come from gaining electrons. So we'll go through that process here in this first example. So we are drawing the Lewis dot diagram showing the formation of the ionic bond in a compound between sodium and chlorine. So sodium is Na. It's in the very first column, so it gets 1 valence electron, 1 dot around it. And chlorine is in the halogen group, so that has 7 valence electrons. So I'm putting 7 dots around chlorine. So I've got 1 atom of each. So that step is done. Now we're going to use arrows to show the electrons moving from the metal to the nonmetal until all atoms are full or empty. So we are going to take it from our sodium, our metal, and give that electron to our non-metal chlorine. But this is also just the easiest way to get our atoms full and empty. I could have moved all 7 of those electrons from chlorine to sodium, but that would be way more arrows and way more crazy. The simplest way to get all my atoms full or empty are to transfer that 1 electron from sodium to chlorine's empty spot there. So that's that step 2. All my atoms now are looking like they're going to be completely full and completely empty. So we're ready for step 3. We're going to redraw these atoms. Sodium is empty in its square brackets, and chlorine is going to have 8 dots around it now that it's gotten that 1 extra one from sodium. And then we give them their charges. Because sodium lost 1 electron, it becomes a positive 1 charge. Because chlorine gained 1 electron, it becomes a negative 1 charge. So this is the process of formation of the bond between sodium and chlorine. Not too bad, right? Well, it's not quite always that simple. This next example isn't that much different, but if we start drawing calcium, which is in the second column, it gets 2 dots around it, and then sulfur is in oxygen's column, column 16, which gets 6 valence electrons, 6 dots. And now that I've got those drawn individually, I'm trying to decide which way I'm going to be drawing my arrows. And it is always the metal to the non-metal, but it's also easier to move these 2 electrons from calcium into sulfur. So we're going to move these into these empty spots that we have here. I'm just making my arrows kind of larger and swoopy to make them clear where they're starting and ending at. And that looks like now calcium will be completely empty. Sulfur is going to be completely full with 8. So a little more arrows, a little bit more movement going on, but not too bad. Keep in mind, because calcium lost 2 electrons, it's now going to be a +2 charge. And because sulfur gained those 2 electrons, it's going to be a -2 charge. But we still got calcium completely empty, sulfur completely full. Now in this next one, we're going to have our potassium and oxygen getting together, and potassium is in the first column just like sodium was, so it gets 1 dot. And then oxygen is back over there in the same column as we saw sulfur in, and so it gets 6 dots. And then if we start trying to move our electrons over, okay, this is pretty normal. Potassium is completely empty now, and yet our oxygen is not completely full. It's not done yet. We can't be done yet because we don't have all of our atoms full or empty. This oxygen is still going to be really reactive and really aggressive about going out there and trying to fill in its one last empty space. That's all it needs to be happy and stable. And so what it's going to do is go find another potassium ion. Since we need another dot, another electron to fill in that space, we're going to draw another atom of potassium in that second step and use its electron to fill in that spot. So this oxygen is going to tend to react with 2 potassiums at a time instead of just one of each in order to get happy and stable with that octet rule. And so when we draw this out, like I had mentioned in that third step, you can use coefficients. We can just say we have 2 Ks that are completely empty, but each of them still has a +1 charge because each potassium still gained or lost 1 electron. Just recoloring that real quick just to stay and follow those rules I said I was going to. And then we have our oxygen, which is going to be full. It did get all 8 electrons that it wanted. Still give it its square brackets, but here because it gained 2 electrons, it's going to have a -2 charge. So if you would prefer here, if it's simpler, if you have a hard time remembering to use those coefficients, like I said before, I don't mind if you just redraw both of those separate K pluses. Each of them are still a +1 because they lost 1 valence electron. So you're basically just redrawing everything you did before, showing kind of the after effect after that electron was transferred to its new atom. So either this or this will work for me. It does not matter either way, as long as you show that final process there. Now, this last one is aluminum and bromine. And if we start drawing aluminum's Lewis dot diagram, it has 3 valence electrons, and our bromine has 7. So there's 1 empty space on that bromine waiting to be filled. We can move 1 of our electrons over into it, but now I have 2 spare electrons. Nowhere to put them. We need more spaces to put these electrons in order for all our atoms to be completely full and completely empty. So I'm going to need another bromine atom. So I'm going to draw another bromine atom. And once I do that, I have another space for another 1 electron, but I still have another electron that needs a spot. So guess what? I need to draw another bromine atom. And now I'm going to have enough spots to put all of my electrons. Now my aluminum is going to be completely empty and all of my bromines are completely full. So that's that process. It's kind of like check and guess and like just keep going until it's there. Once we learn how to draw and write chemical formulas, you won't have to do that as much. You'll know already that this should be AlBr3, which tells you we need 3 bromines with 1 Al. But that's something we'll get to in class together. And you don't technically need those skills to be able to do this. You can still do it without it, but it does help sometimes. So we're going to take that Al, which is now completely empty because it lost 3 electrons. It's going to have a +3 charge. And then we have 3 separate bromines, and each of those bromines is going to be completely full. And because each of them gained 1 electron, they have this -1 charge on it. So hopefully that's not too bad. We'll work a couple more examples of this in class. But you're really only going to see 1 or 2 of these in your future. But this can help us understand what we're about to do in our next class in writing some of the formulas and equations.